Hey guys, my name is Adrienne and welcome to Organic Chemistry 1, Part 2 of these recorded sessions. Today we'll be going over, for most of y'all, Chapter 2, and in general, just acids and bases. These are the topics we'll be going over today: bronzed acids, bases, Ka, factors of acidity, Lewis acids and bases. Um, you can feel free to skip around. I'll have the titles up on each page we do. So find what you're looking for, or feel free to watch all of them, and hopefully that helps. So let's get started with the first topic: Bronsted Lowry acids and bases. So for these are going to be quick summaries of each topic. So if you need more information, definitely go into the book for more details, or um, into Learn Smart if you guys are still doing Learn Smart, things like that. Those are more practice for you. So, but in summary, Bronsted-Lowry acids and bases, we know that Bronsted-Lowry deals with what specific type of atom, right? So these deal with protons, right? So acids are H donors, right, or proton, because we know hydrogens are just protons, and bases are the opposite, hydrogen acceptors. So, with this being said, if you have hydrogens, if you're donating hydrogens, obviously you must have hydrogen, right? So, if a molecule has any type of hydrogen, they're carboxylic acid. If the bases are needing some hydrogen, so like NH3, things like that, or if they can take hydrogens, then that'll make them carboxylic bases. So, just kind of like another way to kind of look for these is that we already said contains H, right? And it can be any charge. Let me move this out of the way. Any charge. But for bases, they don't have, um, they're lacking protons. So they might have like lone pairs, pi bonds, things like that. Basically electrons, right? So because electrons like protons. So these have either lone pairs or pi bonds, and these are either no charge or negatively charged, right? So obviously they won't be positively charged because they're missing that proton, right? So neutral or negatively charged, right? So with these, we know that, we can even go further, and let me change the color and say that if you have hydrogens that you're electron deficient, right? And if you have lone pairs and pi bonds, then obviously electron rich, right? So that's with the acids and bases for Bronsted Lowry, right? And with these, we know, acids and bases make their own reactions. So acid-base reactions, that's what they're called. And it makes sense that hydrogen donors, hydrogen acceptors, acids and bases, they react together, right? And that's just how it goes. And they react with what's opposite to them. And we'll see that again later with the Lewis acids and bases as well. And they're pretty much the same thing, same concept, right? And just another, um, a big point to these is that, especially with Bronsted-Lowry acids and base, is that acidity, that's what we'll be getting to, one of our topics, right? Factors of acidity. Acidity is the willingness to donate a hydrogen, or like we said, a proton, right? I'm gonna start this a lot, right? Because if you think about it, bronzosylary acids are contained containing hydrogens, right? So and they donate those hydrogens. So you're more acidic, the more you give out hydrogens or protons. So that makes sense, right? So now let's do a couple of practices, just to kind of connect the dots. So I'm gonna erase this page and let's do a practice. So bronzosylary still acids and bases. So let's try this one. This one's going to be asking about what, which which one or which ones are both bronzosylary acid and base. So see, and this you're gonna have to pull out your or picture it, I guess, as Lewis structures kind of help you out, or if you already are used to Lewis structures, do it from just in your head. But I think drawing it out, it makes more sense that way. And okay, let me so and then I'll give you this one as well. So here, this one actually label the following reaction. Oh, should have okay. Label the following reaction. So which ones are the acids, bases, things like that. And it yeah. So CH4 HO minus. Great. Okay. So take a minute. You know, which ones do you think they are? And we'll go back. Okay. So I got oops, that one. Kind of missed out. OH, but it's still there. And these two, this is what I got. What about you? So why did we get these two, right? We said bronzed acid, Lowry acids have hydrogens, right? And all four of these have hydrogens, right? So this acid can be passive acid, right? So what makes um the base different? We know the base is what? Electron rich, right? Electron rich meaning it has either lone pairs, pi bonds, right? So this is why I said kind of draw it or Lewis structures or whatever you want to use because for this first one, I think yeah we have enough room. For this first one, CH3OH, right? OH. So it has lone pairs and it has the H to give away, right? And now you might be asking, this one has H's and O. How come it's not this one? Well, let's see. CH3, right? C, and this is how you should have drawn this actually as well. So we have our CH3, CH3, COO, right? So it does have lone pairs and it has pi bond. So why isn't it not both acid and base? Well, there's no hydrogen that can be donated, right? Because we know CH3s, um, you don't really break them. They're not hydrogen bonds. They're just van der Waals, right? And we'll go over that later as well. Um, and you just don't donate those hydrogens. They can't be broken. and carbon is already neutral, right? It already likes those four bonds, so you're not gonna donate that and make it unhappy, right? It's already happy the way it is. You're not gonna break it off to make it unhappy to donate to somewhere else. Does that make sense? If it's already stable, you don't want to make it unstable, right? And and you can kind of see it with H2O here. H here, H here. You might be asking, why is it okay to break those OH bonds, right? Well, oxygen, like we talked about with electronegativity and things like that back in part one, right? It prefers that um, negatively charged ion because it's electronegative. It doesn't mind it, right? Compared to this one, these carbons will definitely mind it, right? It's gonna mind like, why am I negative now? I was neutral. Why don't I stay neutral, right? So that's what you should be looking for. Most of the time, hydrogen bonds are an indication of acids, and that's just the way it is, right? And now with these, so basically this is an N with three um, methyl groups, right? Three CH3s. And you can see here that the same with these CH3s, these CH3s are happy as well, so you're not going to be taking away any of those H's, right? And this N, um, while it does have a lone pair because of that octet rule, right? It's just a base and not an acid, right? So these are both, both. These two over here are just bases, right? So base here, base here. Actually, let me label that for you. Okay. So this is both, and base, base, right? Okay. So what about the second one? So the second one, um, you should have gone, and it's kind of obvious now that since we did the first one, right? That this one is super electron rich, so this would be the base. This one could have been either because we said here both, right? Water can be both, but in this case, it's going to act as the acid because we already have a pretty good base, right? So, and if those are the base and the acid, what would make the product? The conjugates, right? So we didn't talk about the conjugates, but that's pretty much what the product of acid-base reactions, right? And it's just going to be the opposite. If it's a base and the reactant is going to be a conjugate acid on the product side, right? So conjugate acid, conjugate base, and nothing too crazy. It's still the same stuff we have. It's still the same concept. The biggest thing with these, again, is that acidity, which we'll see later, is this tendency to donate those hydrogens. And with reactions like these, looking for those protons, looking for those hydrogens, right? Okay, so with that being said, that's bronzolary acids and bases. Let's move on to Ka and pK, which is not, we don't really have a lot to talk about with these. It's just formulas and trends, but it's still good to know, kind of a refresher, I guess, or a good, I guess, notes, right? K and pKa. And right away, we know that the higher the pKa or the higher the Ka is what, and vice versa, right? So first, let's do some formulas. So pKa is just the negative log of Ka. In organic chemistry, we didn't do a lot of formulas. Um, for the classes I've SI'd, you didn't really have to calculate anything, but just in case your class isn't the one that I've SI'd before. So, so pKa, and then let's see, the other formulas that we have is the equilibrium constant, and then the acidity constant, right? And these you've all seen before, parts of reactants, right? And we have Ka as well. um, H2O, AEQ. So from there you can plug and chug, right? Whatever, what's it called? Whatever numbers are given. And it doesn't get more complicated than that. And the main thing that you're going to be asked about is if it's a higher Ka, what's the acidity like? What's the pH? Things like that. And that's what we'll have here. And this is important, so I'm going to make it a different color. So the higher the Ka, the higher the more acidic, I guess. Higher the acid, and the lower the pH, right? Which makes sense because low pH means more acidic. What about higher the pKa? Equals weaker the acid and higher the pH, right? So again, not too crazy. And also the another important thing, like with bronzolaric acids and bases, like how we said how acidity is the willingness to, give those H's. For equilibrium, equilibrium favors. What do you guys think? What does it? Where would it want to go? Um, if it if an equation asks you in this reaction, in this acid-base reaction, where's equilibrium pointing at, right? So equilibrium always favors weak, weaker acids or high pKa, right? So this is important as well. Um, right. So equilibrium favors weaker acids no matter what. Equilibrium um, goes that direction, right? And that has a lot to do with, you know, who's giving the hydrogen, things like that. You won't see this a lot, but concept questions, why does it do what it does, things like that. So that's all we have for K and pKa. Not too crazy. The green here is the most important, and then the blue here. Hopefully you don't forget it because especially if you're going to professional schools, taking those admissions tests, things like that. That's all they're gonna ask you pretty much. But you don't have to worry about it for you don't have to worry about it too much for OChem, depending on your class, depending on the class you're taking. Okay, so let's move on. So now this is no matter what, even in OChem 2 for the rest of the semester, OChem 1, whatever it might be. It's so easy to forget, but it's so important. This factors of acidity, right? So we have four factors that we have to worry about. One, elemental. And for my own um, notes, I kind of really condensed it into what you look for. So after we list them, we'll go over those. So elemental, inductive, let's see, resonance. So resonance always comes back, right? And four, we have hybridization. So for each of these, they're pretty much, for each of these, focus on different things. Some of them overlap a little bit, but not too much. For elemental, for example, it's all about electronegativity and size, right? So that's why the trend for it is kind of like this is a periodic table, and the trend for acidity increases this way, right? So that's the trend for acidity. But that doesn't always work because inductive is all about how close that electronegative atom is to whatever you're looking for, right? So I always like to label this distance, right? So pretty much if you're this close to oxygen versus this close to oxygen, which how, which one of you would feel it more, right? The one that's super close to you, the one that's like suffocating you, right? Compared to the one that's giving you breathing space. So that's what it's talking about by inductive. Um, if oxygen is not giving you any, is in your personal bubble, you're gonna feel it more, right? You're gonna feel the person or that thing inside your personal bubble more than, feeling them on the other side of the room. So, and for resonance, this one's probably one of the trickier ones, but that's why combined with hybridization, it's not too tricky. So for resonance, it's the delocalization of electrons. This one is all about the conjugate base. So more stable the conjugate base, more acidic, right? Let's see, conjugate base stability. So more stable, more acidic, right? Um, and this ties into hybridization because hybridization is pretty much the S character. Well, it is the S character. So percent S character. So triple bond has more S character than double bond and single bond, right? So the better the S or the higher the percent S character, the more um, acidic. And these two kind of go together because the more S character it has, the more the conjugate base is stable. So, so here I don't have room. Higher S character equals higher conjugate base stability. Stable. Ooh, that's a mess. Okay, right. Okay, so that's what we have for hybridization and resonance, right? And now let's practice it because honestly, this is going to show up even if obviously it's not going to, straight up say, okay, what's going on in this molecule? You kind of just have to think, okay, if I'm thinking about acidity, all of these four have to um, pop into your head: elemental, inductive, resonance, hybridization. And it's probably the easiest to forget as well because, sometimes you're not even talking about acidity or there's no way of telling, you know, there's so much to look for that acidity isn't one of them that you forget. But hopefully you don't forget these because this is probably the once we do the practice, you'll see how kind of simple it is, and maybe it's because it's so simple that you forget it, but it's it's easy to get a hold of. So let's do practice. Factors of acidity. So one, um, which one of these is the strongest acid? And you'll see right away, like, these are just giveaways. CH3, CH3, H2C, CH2, and HCCH. And then let me give you this one. This one is more fun. So you have this molecule, and pretty much it's asking you which which one of these are the most acidic hydrogens, right? So this is going to be, let's put this at 2, 1, and 3. So rank um, from most to least acidic. Okay, and let's do this other one. Oh, do I have room? Yes, I do. So same thing for this one. Well, actually, let's do this one from least to most acidic. Rank from least to most acidic. So let me see. Okay. Okay. So take a couple of minutes and answer these three. Let me finish this one. Okay, I'm cutting it close. Okay, there, there. Okay, and rank these. Oh, this is one, two, three, four. Okay, so let's see, what color should we do? Okay, strongest acid. First one is a no-brainer, right? That's just the hybridization, the S character, and the triple bond. So whatever, right? So what about the second one? I got from most three, two, one. And this also deals with hybridization, right? Because triple bond over here, right? Double bond over here. Here is just single bonds, right? So these two are due to hybridization, right? So what about the third one? The third one, you should have had it ranked as one is the least acidic, four, three, and two. This is the order you should have had. And this one does not deal with hybridization, but instead deals with what? Deals with elemental, right? Because we're dealing with fluorine. This one has nothing. Well, I guess we can put like H here, right? Imaginary H. It is bonded to H. So hydrogen, fluorine, chlorine to bromine, right? So not too crazy. Elemental. Pretty easy to kind of differentiate, right? So it's very easy to kind of get used to. So, but again, right, like I said, don't forget it, right? Because it'll come back a lot, especially when we start doing reactions. Okay, so that's enough of that, and let's go to last one: Lewis acids and bases. So we said that Bronzolari dealt with hydrogens and protons, right? Well, Lewis acids and bases deals with electrons, but pretty much the same concept. So acids, bases. Acids are the electron acceptor, and bases are the electron donor. And if you think about it, it's pretty much the same as Bronzolari acids and bases, right? So with this is also again electron deficient, right? Same as the Bronzolari acid. Let's see, electron deficient and donor electron rich, meaning it has lone pairs or pi bonds, right? Pretty much exact same thing as Bronzolari base. So electron rich, right? So lone pair or pi bond, right? So it can be negatively charged, neutral, whatever as well, right? So or negatively charged. But with Lewis acids and bases, now we getting introduced to another concept, electrophilicity and nucleophilicity, right? So acids, because they want those electrons, they accept electrons, are electrophiles. Electrophiles. And bases, um, they donate, so they're neutrophils or nucleophiles. I mean, nucleophiles, nucleophile, right? Which makes sense. Because if you have electrons, obviously you would want protons making you nucleophile, right? So now with these same concepts, how to determine if a acid or a base is lowest acid base, and again with the introduction of electrophile and nucleophiles, that's what you're looking for. So again, since we kind of know the concept, let's go ahead and do a practice, and it'll make better sense. I feel like. Okay, so let's do kind of like the same types of questions we did. Which ones are both fluid, acid, and base? So H2O, CCl4, H triple bonded. Okay, so which one of those? All of them, none of them, just some of them. And let's see. And let's do a label one. Label this reaction FeBr3, Br4 minus, and then plus Br plus. Okay, and then last one, let's do this. And there's no number for them. Actually, let's number them. So, which one of these are nucleophilic and which one of these are electrophilic? Okay, so this one, this one. Okay, so take a minute and answer those for me. Okay, so both Lewis acids and bases, you should have gotten H2O, this, and this carbon, right? And why? Well, we know H2O was the same with bronzolari acid and base, right? Could be an acceptor or a donor for H's, which means same thing for electrons. Um, here, this is electron rich, right? This C here, but at the same time, you know, these carbons are nucleophiles and electrophiles as well, right? Because the triple bond is just pulling those away from each other. Okay, and over here, you know, it has the electron-rich site, and it's kind of like this molecule over here, I guess. Electron-rich site. Oh, now that I pointed that out, then we'll know what this is. And it's also because this over here, this where it's pointing to, is electrophilic, right? So I'll put E here. E here. And this one, this side over here, the double bond, is nucleophilic because it's electron rich, right? And this is electron poor, um, electron deficient over here because all the electrons are going towards oxygen and going towards Cl, right? Because these two are very electronegative, they're taking away this carbon's electron density. So now for over here, which one of these are Lewis acid base, blah, blah, blah. So you should have gotten acid here, base, and then same thing with bronzolari, they're conjugates, right? So conjugate acid, conjugate base, right? So it's pretty similar to bronzolari acid base. In fact, it's it's like exactly the same except for with Lewis acids and bases. This is what we mostly use because of, it has everything plus electrophilic and nucleophilic, right? So we use Lewis acids and bases more, and they're important because things like these, right? These are these are just skeletal structures, but you know that there's an electrophilic site and there's a nucleophilic site. And the important thing about those is that those are where their reactions are happening, right? Those are where they're going to happen. that's where you're going to be spending a lot of time on, right? Finding those and, you know, drawing arrows, remaking them, blah, blah, blah. So that's all I have for you guys. And again, these are the topics that we covered. Feel free to look for them. And hopefully, you know, you guys learned something. Hopefully that helped. And hopefully it wasn't too crazy. This chapter was, or this part, I guess, to be more, um, you know, broad, is very short. So, it's not too crazy. So, I'll see you guys on the next video. And you guys have a good one.